SI units, they're basically standard physical units used to describe physical quantities in physics. These are kilograms, so kg, which measures mass. There's 7 of them. Moles used to measure chemical qualities, so that's mole. They're also used in physics. There are amperes, which are used to be able to measure current. There are seconds, which are used to measure speed. There are Kelvin and candela, Kelvin with a K, and candela, which are, well, considering they sound a lot alike, that also makes them easier to remember. Kelvin is temperature, we don't use degree, well, we use degrees, but we don't use degrees Celsius. And candela is luminosity extent, I guess. Then there's meters. Very self-explanatory there. Meters. So there are 7 base units, and they all make up other units, which are stuff such as joules, coulombs, current, etc. So say you were to combine units, you could get stuff such as pascals, Tesla, volt, coulombs, hertz. Hertz is frequency, Tesla's magnetic flux density, if you know, forming as F-bill, that kind of stuff. So those are very useful. They're like the basics of physics. Standard prefixes, these are the things which like measure, like they're like nano, so technical difficulties, nano, micro, milli, centi, and then kilo, mega, giga. You literally just memorize an order. Mega, giga. It helps if you do computing, etc. So nano is 10 to the minus 9. These are all 10. They're all used in standard form. Standard form is a way of representing very large or very small numbers. So basically stuff which like the speed of light, etc. They're very useful to be measured in standard form. Micro is 10 to the minus 6. Milli is 10 to the minus 3. Centi 10 to the minus 2. And then it just goes 3, 6, 9. So nano, micro, and milli are literally just opposites of micro, mega, and giga. And then just remember centis minus 2. So say you have 1 second. That means that would be 100 centiseconds, because obviously 10 to the minus 2. So you times it by 100. So those are the prefixes, and they're useful to be able to measure like smaller quantities, so you don't need to use like massive numbers to be able to represent most stuff. To be able to convert units, first you need to find the ratio. The ratio would be the ratio from the thing you're converting to the thing you want to convert to. So say if you were to go from meters to kilometers, then the ratio from meters to kilometers is 1,000 meters equals 1 kilometer. So you divide by 1,000. So the basic principle is, say you have 1 meter and you were to convert that into kilometers. The basic principle is times 1 kilometer by 1,000 meters, and that literally gives you an answer of 0.0012 that. But that's the basic principle. So like say you are still putting 1 kilometer here, but basically it's very self-explanatory. You just divide by 1,000, but then that's not really how you're meant to set it out, I guess. So say if you were to convert 1,600 meters into kilometers, 1,600 meters into kilometers, so obviously that is like simple maths, but when you want to actually do an exam, you have to do 1 over 1,000. That 1,000 is a meters, and that 1 is a 1 kilometer, and that's 1.6. Right, physical measurements and their limitations as well as errors. So basically, physical measurements are like things which you take a measurement of, and the measurement model is basically the idea that what you see, so say your eye, is the observed value, and what your eye sees is a true value plus an error. Most predominantly, these errors are two types. One is a random and one is a systematic. So basically, the random error is stuff which change all the time. Like every time you do it, it will change. That's because it's going to be something to do with how you see. So say this is your eye and this is a ruler. This is a single point. This is where something's putting down. If your eye was here, you'd see a different angle to directly on top and then here. So theoretically, this point would also always be different from whatever angle you're looking at. That would be the random error. So if you do a large range of measurements, etc., it would kind of even out the error. Whereas systematic errors are not random. They follow a pattern, and this pattern is predominantly stuff like a lack of you haven't calibrated your apparatus, etc. Calibration is basically when, like, say you have something, so you have a scale, and you have a thing on top of the scale, so let's say a human, and you know the human's weight is 79 kg. So basically, when you definitively know the weight is 79 kg, and the scale comes up with something such as a 2, you know there's a systematic error. So if you take that 3 kilos into your head when you're doing the calculations, that means that you have calibrated your apparatus and that technically you have eliminated that error. So obviously the formula for an error is observed value equals true value plus error. Systematic errors can be measured in different ways. So basically the main way is on a graph. Say you know the graph is meant to look like this, with the y-intercept being at 0, but say the graph starts like that. You know that that part of the graph is the error, is the point at which it shouldn't actually be there. Another way to measure errors on a graph is through the use of error bars. So that is here, and then say that, and that. This isn't really errors in a way, this is uncertainty. So the idea of this is however bigger the error bar is, that's how much more uncertain you are of an actual value. The smaller the error bar, the better the understanding of the value. The formula for uncertainty is range over 2, and when you have no range is the resolution. So the resolution is basically maximum or minimum precision. So plus or minus, it will normally be like 1 or 0.1, etc., going down in that kind of magnitude. So yeah, error bars, and the formula for uncertainty is range over 2. So there are 3 types of uncertainty which needs to be known about. So there is absolute, there is fractional, and there is percentage. Percentage uncertainty is basically when absolute uncertainty is the definitive location. So you know something's 140 plus or minus 5. So the absolute uncertainty is at plus or minus 5. Fractional uncertainty is at 5 over 140, because it is the absolute uncertainty divided by the actual value. And the percentage uncertainty is 5 over 140 times 100, but it's the fractional uncertainty as a percentage basically. And that is the 3 types of uncertainty. Estimation is another thing. Estimation is basically the process of estimating really is the process of guessing something that's gonna happen sooner or later. And estimation normally falls under the category of using it's using magnitude. It's a process of using the order of magnitude. So the order of magnitude is basically, say you have a human here, and then you have a house which is that big. The order of magnitude for a human would be 1 meter, while the order of magnitude for a house would be 10 meters. That's because the house is obviously much bigger than the human, thus the obviously much bigger order of magnitude. This would be the same for age, in which you would use 10 for teenagers or then higher as you go up. These order of magnitudes are values of 10, and they are useful when trying to refer to a value which is most close to approximate it, and that is estimation in this topic.